Hi, so today I'm going to explain how I implemented a queue-like structure using two stacks, and if you know, this is the exact opposite of the last Fun Friday that we did. And so here I created two stacks, and I'm going to move all of my elements from stack 1 to stack 2, and I'm going to do that by using push, and then pushing in that top element of the first stack, and then popping popping another element from the first stack, and keep doing that until that stack is empty, and then I'm going to push my new value into my first stack, and then push everything back into from the second stack to the first stack, right? And I'm gonna kind of explain all of how this works in a little bit. And then for dequeue, it's very simple. It's really similar to how you would pop a stack, obviously, because we're using stacks. And so if it's not empty, then you're gonna save your top and pop out your top. And I just return X so you can see kind of what I'm going to do later. And for this size in front, I'm basically using the built-in stack functions that they have. And then, so I'm going to show you guys, obviously, how this kind of all works together. So, obviously, I enqueued 1, 2, 3, and within my stack, 1 is at the bottom, and 3 is at the top. But in a queue, 1 is supposed to be at the top, in a sense, or the front, and 3 is supposed to be in the back. And kind of a part that I forgot to introduce is what queues really is and how it's very different from stacks. A queue is first in, first out, whereas a stack is first in, last out. And it's very interesting using stacks to enqueue something, to use stacks to kind of replicate a queue, because, you know, they're very different in the sense of kind of what I just described. But I'm going to show you guys how this all kind of works out. And so I'm enqueuing or putting into my stack actually 1, 2, and 3. But for an actual queue, obviously, you would, well, I don't want to cause a compiler error, but you would have 1, 2, 3 with 1 at the front, right? But when I dequeue, to actually stimulate that that queue-like structure, I want to be able to pop 1 out. I want 1 to be the first thing I pop out because I want it to be the first thing on my first stack. Yeah. And so as you can see, I do end up dequeuing in the right order. So actually this will pop in like this. It will look something like this. Starting out, it will be 1, 2, and then 3. And then when I switch it to my second list, and then switch it back to my first list, it'll come out to be like this. 1, 2, 3. And that way I'm actually dequeuing from the very top and then going all the way to the bottom, similar to how a queue would be. And that's basically it, but just so you know that my size and front work, I'm getting the front to the very top, so it should be 1, and my size should be 3 because I'm enqueuing 3 things. So once that runs, you'll see like how that all works out. Sorry, it is Replit, so the compiler is a little slow. Okay, perfect. So it's kind of showing me exactly what I want. So this is the end of part 1 for my video. Sorry, I completely forgot to talk about time complexity, but I'm going to do that real quick with my functions. So from what I remember, enqueue is O of n, because in reality you don't really know how many times you're going to be pushing and popping, popping and then pushing into your second stack. And so that's something that, you know, you don't know, so it can't be O of 1. similar to what a push and pop would be in a stack. And then for DQ, actually, it'll be O of 1 because you're actually only popping out the very top of your stack or the very front of your queue once it's sorted. So you know exactly that you're only going to pop once. So it's a constant, so O of 1. So yeah, sorry about that. And so now I'm going to start explaining the second part, and the second part is explaining BFS, or breadth first search, and that's something that is really useful in a lot of ways and we can see applicable in a lot of situations. But first I'm going to start off by explaining the definition and how it kind of works. So this algorithm actually starts traversing the root node and then explores the neighboring nodes. And it kind of follows that same process for each node until it follows the goal. And kind of when I talk about nodes, kind of imagine almost like a tree. So let's call this A, and let's do this B, and let's do C. And this is a very, very simple way of kind of showing what this is, but I think that's kind of the best way to do it, especially starting out. But basically you'll have an output. Oh, and also this algorithm uses queues in order to process, and this is my queue. So I'm going to show you how queues are used. Sorry for the horrible handwriting, I am working on my Mac. So here's my output, right? So I'm going to start with my root node, which is A. So this is my output, right? But in my queue, I'm going to put B and C because those are my neighboring nodes, so that I know to go there after I'm done with A. So now I'm done with A, I've outputted it. So now I have to go B and C. And let's just do this. And let's kind of make this complicated so you can kind of see more of what this is actually doing. Let's make this D, make this E, and then, sorry, and then let's make this F, right? Okay. And so now that I've gone through B and C, I'm going to keep in track what's near B and C. So I'm going to be done with this, and the next in my queue is D, right? And then I'm gonna D, be done with that, and then E, which is near C. But since we already outputted that, right? Take this out and just do F. And here, yeah, that's your output. And basically you can kind of see how it starts at the very root node, aka in this situation A, or if it was a tree, your very top node, and then it starts exploring. It starts at your root node and then it adds the neighboring nodes to your queue so you don't forget to go there and output those neighboring nodes after you finish with A. And it keeps doing that until until it outputs exactly what you want, in a sense. And so an example of this would definitely be so searching up Wikipedia, right? And then following that Wikipedia page and seeing links and adding those links to the queue so you don't forget to look at those citations, and then going to those links and looking at more links at those documents and keep going and going and going until you are satisfied with your result. And that's kind of BFS in an example type situation. And yeah, so that's the end of my part 2.